Good morning. Today we're going to start with rocks, and you should have downloaded the list of questions as review so that as you watch the video, you can proceed to answer the questions. We're going to start with rocks. We've just finished minerals. We talked about criteria for something being considered a mineral, like being a solid, naturally occurring, as some of the criteria. We also talked about groups of minerals. We talked about silicates, carbonates, oxides, native elements, and then we talked about some minerals that we referred to as rock-forming minerals. Those minerals that we commonly find in rocks, and so that's where we're going to start today, with rocks. You see this is a picture of a rock. You may not know the name of it, but it is granite. And you see these large crystals here? These crystals that I'm pointing to are examples of minerals, because minerals are the things that make up rocks. Common rock-forming minerals include the ones that you see here: feldspar, quartz, biotite, muscovite. Those are the types of mica. Olivine, hornblende, and pyroxene. Feldspar and quartz are on the list, and so that's the most abundant silicate mineral, and this is the second most abundant. And it so happens that these common rock-forming minerals listed here are all silicate minerals. So that means that they have something in common. And we know what the building blocks of all silicate minerals would be. It's the silicon-oxygen tetrahedron. There are three types of rocks: igneous, which we refer to sometimes as fire rocks that are formed from magma or lava. Hot, melted rock material, either below the surface of the earth or on the earth. Sedimentary rocks, which by definition, if we look at the term, we can think that sedimentary rocks are made from bits of sediment cemented together, and in a lot of cases they are. And then metamorphic rocks are formed from other rocks. Those rocks, which could have been igneous rocks, they could have been sedimentary rocks. When they're exposed to heat, pressure, and chemicals, they can become metamorphic rocks. And some rocks that have already changed, that are metamorphic rocks, when they're exposed to more heat and pressure, can become another metamorphic rock. But for our lecture today, we're going to only talk about how igneous rocks are formed, and we're going to talk about two ways that they can be classified. Now, the formation of igneous rocks, remember I told you that igneous rocks are formed from melted rock material below the surface of the earth, or they are formed from molten material on the surface of the earth. If the molten material cools and solidifies, and the molten material is below the surface of the earth, it's called magma. If it's on the surface of the earth, it's called lava. And the rocks that are formed when the magma cools and solidifies are called intrusive rocks or plutonic rocks. They are called intrusive because they are formed below the surface of the earth, but inside the interior of the earth. Those that are formed from lava are called extrusive or volcanic igneous rocks. Intrusive igneous rocks, remember, they're formed far below the surface of the earth. And if this is melted rock material below the surface of the earth, that means that the cooling rate is going to be slow. And so there will be large crystals. Look at the granite here. See the large crystals? And those large crystals are specks, as we may sometimes call them, are the minerals that make it up. All right, then there are extrusive igneous rocks. These cool quickly. And so they have small crystals. Extrusive igneous rocks can have small crystals or no crystals at all. This one has small crystals. And look at them side by side. This one is extrusive. This one intrusive. Cooling rate is different. And because they have different cooling rate, you can see they have different size crystals. This little chart, you have one of those diagrams in your book, one similar to this. This shows, well, I'll move too far. This shows the cooling rates. Intrusive igneous rocks, slow cooling. This magma far below the surface of the earth. And when it starts to cool, it takes a while. So that gives an opportunity for crystals to grow larger as the magma starts moving upward. Then the cooling rate is going to decrease. And as the cooling rate decreases, that means that the crystal sizes are going to also decrease. So we have medium-sized crystals. All right, let's move this magma up and get it out so that it can come out of the volcano. And when it does, it's going to cool fast. And when it cools fast or extremely fast, we will get extrusive igneous rocks, some of which may have small crystals and some no crystals at all. So let's talk now about classification of igneous rocks. One way to classify them is by texture. And I know we have a tendency to think of texture as the way something feels, but when we talk about rocks, we're talking about the size of the crystals. And the size of the crystals of igneous rocks, we know is based on the cooling rate. Remember the diagram that I just showed you? Slow cooling, large crystals. And then we can classify igneous rocks by mineral composition. Now, same diagram again for difference in the textures that we will get based on cooling rate. Here are the examples of the textures and the names that we have for them. Coarse grain texture, or we can say fine grain texture. Now, if you look at this, you can see large crystals here. So if there are large crystals and you're able to see these different specks, that means that this was slow cooling. So this coarse grain igneous rock, based on its texture, is also intrusive because in order for those crystals to grow large, the magma was far below the surface of the earth. And here's a fine grain texture. Fine grain textured igneous rocks are also, we can refer to them as extrusive. Then we have medium grain igneous rocks, and they have a medium cooling rate. And you saw that on the diagram that I showed you, where the coarse grain igneous rocks, large crystals, as the magma moves up, the cooling rate decreases, the crystals are going to get smaller. And so that's the medium-sized crystals. And then we have glassy igneous rocks. The lava cools extremely fast, so fast until there are no crystals at all. And here are some examples. Look at the medium grain here. And then glassy, no crystals at all. You probably recognize the one on the right as obsidian, and this medium grain one that's on your left, it happened to be a granite. And then we have vesicular texture, and that's one that's classified by the rocks having tiny vesicles or cavities at its surface and on the inside. And another type is porphyritic texture. Now, when you read what I put up here, it says when the magma has been slowly cooling within the interior of the earth. Well, if it has been slowly cooling within the interior of the earth, that means that the crystals are going to be large. But then as that magma suddenly erupts at the surface, that means anything else in there in that molten material will cool fast. And so that will give you then small crystals. So look at that. Porphyritic, we call that texture porphyritic. Look, large crystals. These large crystals occurred when the magma was far below the surface of the earth. And so they had an opportunity to grow large. And then when that magma erupted on the surface of the earth, it began to cool faster. And so we get these small crystals. And when you read in your textbook, you will see that the small crystals are often referred to as the ground mass. And here is the vesicular texture, these tiny holes. And this happens to be an example of basalt, vesicular basalt. And that takes care of texture, which had to do with the cooling rate. We can have coarse grain, we can have porphyritic, we can have fine grain, medium grain, we can also have glassy. And there are other types of textures too, but these are the ones that we have mentioned. Now, when we classify the igneous rocks by composition, that has to do with the minerals that make them up. So we're going to talk about 3 different ones: felsic or granitic. If it's felsic, if you look at the term, felsic should remind you of the first 3 letters, should remind you of the most abundant silicate mineral, and that is feldspar. And so felsic igneous rocks have an abundance of feldspar and quartz in them. And since the most abundant felsic igneous rock is granite, sometimes that group is also referred to as granitic. Well, what are some characteristics of this group? They're light in color. That's because they have an abundance of quartz and feldspar. 2 examples of rocks are granite and rhyolite. Now look at granite and rhyolite. Here, this is the feldspar, and the glassy looking stuff is quartz. You have a whole lot of quartz and feldspar in it. That's why it's light in color. Rhyolite also has a lot of quartz and feldspar in it. You are looking at 2 different rocks. And let's back up for a minute and see what else do we know about these rocks. They don't have the same size crystals. So if they don't have the same size crystals, that means that they do not have the same cooling rate, or we can say that they do not have the same textures. And then we have mafic or basaltic igneous rocks, and the most common one in this group is basalt. And these are dark in color, and they contain minerals that are higher in iron and magnesium. And minerals high in iron and magnesium would include minerals like hornblende, pyroxene, biotite mica would be examples of these, and olivine. And they also have high densities. Look at the 2 examples, gabbro and basalt, dark in color, but you can look at the gabbro and see that gabbro has large crystals. So thinking about something that we learned early in the video, we can see that gabbro and basalt have the same composition, but they have different textures. You can see the crystals easily in gabbro, but you can't see them as readily in basalt. So the cooling rates were different. And then we have some that are intermediate or andesitic. And they're intermediate because those rocks in this group, based on their composition, they are going to be darker than the felsic rocks, but lighter than the ones that are basaltic. And that's because, and the reason for that is they contain some darker minerals rich in iron and magnesium. And then they also find lighter minerals that can be found in the felsic rocks. And examples would be feldspar as one of the examples. 2 of the rocks would be diorite and andesite. See, diorite, andesite. Those are the ones that are intermediate. And based on what I showed you, oh, here I go again. Based on what I showed you about cooling rates, and also about the composition, these 2 have the same composition, a different cooling rate, and therefore they have a different texture. Now, this will help us to put it all together. Chemical composition across the top, granitic or felsic, light in color, andesitic, intermediate, and then basaltic. All right, and I didn't do ultramafic because the only rocks that we can think of at the most of the time is the one that makes up a part of the mantle in the earth. So we're going to do these common ones here. So these are the composition. This tells us the dominant minerals. Amphibole is written here. That's what we sometimes refer to as hornblende. Pyroxene is augite. Now, if you look at these, this refers to the texture. And so granite and rhyolite have the same composition. They're both felsic, but granite and rhyolite have a different texture. Fine grain, coarse grain. All right, now, let's figure out the things that are alike about these three rocks, granite, diorite, and gabbro. They are alike because they are coarse grain. They have the same texture. All right, what's alike about rhyolite, andesite, and basalt? Same thing, texture. But even though granite and rhyolite have the same composition, they have a different texture. Their textures are different because of their cooling rates. Same thing for diorite and andesite, gabbro and basalt. So we can say gabbro and basalt have the same composition, but gabbro and basalt have a different texture. Texture again is related to cooling rate, and the color of the rock and the composition has to do with the minerals that they contain. All right, for Bond reaction series, when I show you the diagram that's next, you're going to remember having seen that in your textbook within chapter 3. That shows the sequence in which minerals crystallize from a cooling mafic magma if the crystals are removed during the cooling rate. All right, now let's look at that. If you look at this diagram, you can see that this talks about the cooling of the magma. This is low temperature, relatively low temperature, and I need to back up. My computer is so sensitive, can lightly touch something and it moves. All right, and this is high temperature. All right, now if you look at this chart, Bourne reaction series, you can see that olivine is the first mineral to crystallize. And if you want to know, looking at this chart, the minerals that are found in basalt or gabbro, just look. That's pleasure clays feldspar. You can see what some of the minerals are. Also has some biotite, some hornblende, pyroxene, and olivine. Okay, but let's go down to felsic, granite and rhyolite. Look at these minerals. Have a lot of potassium feldspar, muscovite mica, and quartz. So you can see that they have an abundance of minerals that are light in color. This diagram shows the temperature based at which the minerals will, the order in which, the minerals will crystallize out. And the first one to crystallize out is olivine. Now you probably took a look at these questions and have already started to answer them. And so go ahead and continue to work on those. And the next time I talk to you, it will be on sedimentary rocks.